very much. So it is a pleasure to be here. Thank you very much to the organizers for inviting me to give a series of lectures in a place which is called Center for the Study of Rationality. That's something.
It's a building.
Yeah. Okay, so
different floor.
also because of that, the title of my lectures is called, it includes very old black holes. So I should explain what I mean by very old. So if you think about the black holes that exist out there in nature that we are studying experimentally now, they of course are old, but they are not older than Hubble time, more or less, 10 to the 10 years. But if you left them to evaporate freely, they would evaporate in times which are of the order of between 10 to the 70 or 10 to the 100 Hubble times, which is pretty big compared to the age of the universe. Okay? So evaporation time will be for me a very small amount of time. So in these lectures I'm going to talk about time scales which are exponential in evaporation time. So exponential of 10 to the 100 Hubble times, or exponential of the exponential of that. And having said that, you may think that I'm not worthy of talking in this place for the study of rationality, okay? Because it's like what physical problem could depend on that, right? I mean, there are some problems which are inherently dealing with a priori infinite time scales, like for example eternal inflation. But it's much less obvious that the study of black holes involves that question precisely because of the issue of the evaporation of the black holes, which occurs on a time scale which is smaller. So what I'm going to do in this first lecture is to tell you about some standard arguments, very briefly, about why these time scales are interesting for the case of black holes. Why should we worry about them? Why should we study these time scales? Okay. These are kind of standard arguments. I will go through them with a high brow. So if you want to interrupt with questions, we can just make it into a more interactive discussion. Right? So everything I'm going to say is probably well known to all of you in this lecture. So I'm going to review, let's say, time scales. In black hole dynamics. So first of all, the black hole is here. This is my black hole, has a size r. And because it is a black hole, it has a relation between its mass and its radius. And this relation, in 4 dimensions, for example, is the famous GM of order r. Okay? In general relativity, this thing is much more sharp, because the solution for the black hole, as you all know, has this form. If I am working in d+1 dimensions, then this function f of r has this form, 1 minus mu over r d minus 2. And this mu is a parameter which is given by 16 pi g m divided by d minus 1, the volume of the unit sphere in dimensional dimensions. Okay? And then the radius of the black hole is defined as the point where this function vanishes. So r is equal to mu 1 over d minus 2. And you know that this has a significant sharp interpretation in terms of the causal structure of space-time. So what happens is that there is this region which is at radius r equal r, on which the light cones tumble. Okay, so light cones are okay here. This is the time direction. But here the light cones tumble. And then if you enter in this region, you are forced in a finite time to fall into a singularity. Okay? This black hole could have formed in some prosaic manner by collapse of matter, like this. And then we speak of the horizon of the black hole as the set of trajectories, if you like, of the last light rays that can escape. Okay? So this includes regions in which there is no curvature. Okay, so there is a classical time scale which is obvious, which is just R, which is the time scale for any relativistic effect that occurs in the vicinity of a black hole. And it's also the time scale for the free fall time of an observer from the horizon to the singularity. Okay? And it's also the time scale for the free fall time, the proper time, of anybody who is falling into the black hole from the region in which the relativistic effects are important. Okay? So those are obvious time scales, the classical time scales. There is another one which is less obvious, which is called kappa, which is the inverse relaxation time. So if you like T relaxation, it's going to be 1 over kappa. And this has to do with the following. This has to do with looking at the horizon very close, locally. Okay? So if you look at the horizon locally, what you see is just like a plane. And you are here. Right? So you can expand the metric in Taylor expansion near the horizon. So you take this function f of r, and you write it as twice kappa r minus r plus higher order corrections. So kappa is just 1/2 of the derivative at the horizon. And this is d minus 2 over 2, 1 over r. This quantity is also called normally the surface gravity. And it has some mechanical interpretations, but I'm interested here in some other thing. Let's consider now null geodesics, which are radial, in this region. So the metric in this region you can write down in a different set of coordinates in this form: kappa square rho square dt squared minus plus d rho squared plus r squared d omega squared. And this is the famous Rindler form of the metric, where rho is just proper distance from the horizon. So rho is proper distance. Okay. So so in this form of the metric, you can see that if you take, for example, radial null geodesics, then the equation they satisfy takes this form. It's given by d rho d tau equal plus or minus kappa rho. And then the solutions of these are exponentials. Okay? So if I make a plot here now, this is the horizon, this is rho, this is t, and then the solutions are of the form rho of t equal to kappa to the minus 1 e to the plus or minus kappa t minus t0. Okay? So t0 is the time the geodesics enter the region which is what I will call the relaxation zone of the horizon, which is the region which is bounded by rho less than kappa to the minus 1. Okay? Is roughly the region below which this approximation is good. So you have this relaxation zone here. And then the geodesics look like this. They are exponentials like that or like that. And T0 is just the time they enter or come out of the relaxation zone. Okay? So what you see is that if you just have one of these geodesics, for example, one that is going in, you see something very familiar, which is that if you look at how this looks in time, with respect to this time t, which is the time that is appropriate for the external observer, then everything gets exponentially pancaked into the horizon. Okay? So the vicinity of the horizon is cleaned up exponentially fast. Right? So things cleared up from vicinity of horizon with characteristic time scale kappa to the minus 1, right? Which solution? Yeah, the other solution corresponds to something that is coming out of the black hole, which is a very unusual situation, of course, because normally things don't come out of the black hole. Okay? But I will actually say something about it in a second. And this is what is behind the no-hair property of the black holes, because if you consider, for example, now fields here, classical fields here, and you imagine that they have features, they have crests, for example, these wave crests will just tend to fall at this rate to the horizon. They will pancake on the horizon in this with respect to this time variable. And then the tails will go down at this rate because the part of the field which is of order 1, say, moves to the horizon. Okay? So let's say that you have perturbations that come, for example, from the process which made the black hole. Okay? So you have some transients, you made the black hole, you have the metric has order 1 features there, but then you look asymptotically at how the fields and the metric in particular looks near the horizon, and what you find is that all the details of the things that are corrections to the Schwarzschild geometry tend to fall along these trajectories, and when you look at them at some given distance, only exponentially small effects should remain. So you have some perturbation in some field at time t divided by the perturbation at time 0. This I will call the memory. This should go as e to the minus kappa t. Okay? And this is what the no-hair property means in practice. This is just a heuristic way of seeing. Okay? So these are the classical time scales, which are all of order the size of the black hole for dynamics near the black hole horizon. What about quantum time scales? So of course, there is an obvious one, which is just the fact that the black hole is going to operate by emitting quanta, and these quanta are emitted predominantly in a wavelength which is of the order of the size of the black hole, right? So lambda for each quantum that you emit is of order 1 over omega. Omega is the energy, and this will scale like r. Okay. Moreover, we know that they are emitted with a thermal spectrum. So there is a temperature which is associated to them, which when you calculate it, comes out to be exactly kappa over 2 pi. And this is a general formula which is valid for black holes which are charged or rotating or whatever. Black holes which are more general than the ones that I consider in this example. So there is a natural time scale, which is the time scale for emission, for quanta emission, which is of the order of r. So 1 quantum comes out every r seconds from the black hole. Okay? Now that means that there is automatically associated another time scale, which is the evaporation time scale. The black hole will gradually shrink. So if you have a black hole of mass m, since the quanta have an energy of order omega, the number of emissions is of order m over omega, number of quanta emitted, and this thing is of order m times r. And this should be of the order of the entropy of the radiation that comes out, okay? Because it's the number of quanta. So this should be of the order of the entropy. And indeed, if you define the entropy of a black hole from the classical formula from thermodynamics, which is what Hawking did, so you define the entropy of a black hole as a function of the mass by integrating dm over t as a function of m. When you give the formula for t in terms of m, what you get is the famous area of the horizon divided by 4g, which is the area of the horizon divided by 4 L Planck squared in 4 dimensions. This is in 4 dimensions. And this is case like m times r, okay, which is the quantity that we have here. So that means that the black hole will evaporate in a time which is linear in S, okay? So the evaporation time will be of order r, which is the time it takes to emit one quantum, times S. And that's a very large time scale, okay? And it is also a time scale which is non-perturbative in the Newton constant, because this goes like r times the area divided by g, okay? Now, what goes into deriving more carefully all these things? What goes into that is what goes into deriving the Hawking formula. And what goes into deriving the Hawking formula is the assumption, basically, that if you look at the horizon at late times and you neglect memory effects, that is effects of order e to the minus kappa t that perturb the background, okay? Then if you consider quantum field theory in the vicinity of the horizon, you should see that locally you are seeing the vacuum state, okay? So you postulate that the horizon is smooth. That is what implies, if you like, the equivalence principle. If you are looking through the horizon in free fall, you see the vacuum, okay? And if you have quantum fields there, you see the characteristic fluctuations of the quantum fields in the vacuum. So that means in practice that if you consider, for example, here correlation functions of local operators, they should behave like Minkowski correlation functions for delta x going to 0. So when the separations between the operators become small, they should have the asymptotics of quantum field theory in flat space. That's the assumption that goes behind the calculations of Hawking. Another way of saying this is that the wave function of the fields, if you analyze it locally here, will just look like the wave function of quantum fields in Minkowski space, right? Now, that includes maybe quantum field theories that are strongly coupled. The important thing is that the horizon is smooth. So gravity is treated perturbatively, and gravitons are treated perturbatively. So, of course, you have Einstein gravity around here. You cannot neglect it. But what you do is you treat gravitons perturbatively in a series expansion in terms of the Newton constant, like an effective theory. So you use effective field theory to account for gravity. That means that there is an expansion parameter of your dynamics, which is proportional to Newton constant, okay? And you need to form, to characterize the expansion parameter of your dynamics, you need to form a dimensionless quantity, an effective coupling. And the natural effective coupling is the energy, is governed by the characteristic energy of the quanta that you are emitting, because the characteristic energy is 1 over r, since the Newton constant in d minus 1 dimensions, d plus 1 dimensions has dimensions d minus 1, so 2 less than the space-time, then the expansion parameter is given by this quantity. And this is precisely 1 over s. Okay? So if you have a black hole which is large, s will be huge, say 10 to the 70, okay? Which means that the expansion parameter is extremely small. So it's very good. Okay, this expansion is better even than QED. All right. So this effective field theory is what goes into the this effective field theory treatment is what goes into the derivation of these things. Okay, and in particular, the fact that gravity is a non-renormalizable theory is not bothersome, provided you treat it according to the rules of effective field theory, which means that you only stay within perturbative finite orders in 1 over s. So you expand every quantity in finite order expansion in terms of lambda effective, so finite orders in 1 over s, and then you only need a finite number of counter terms to absorb the divergences. It's just like when you use the theory of pions, for example. Okay? Of course, if you want more precision and you want more terms, then you need more counter terms, and you have the problem of non-normalizable theories. Otherwise, you have to use a string theory or something more powerful. Okay? On the other hand, in a string theory, normally you don't control local quantities. So these kind of questions about what happens near the horizon, things like that, are not easy to translate into the formalism of string theory, even if you have a description of the problem of a black hole in string theory. Okay? So notice that because you are expanding in the limit in which S is very large, technically, this is an expansion about S equal infinity. Okay? So it's an expansion in which you take the mass to infinity, the Newton constant to 0, and you keep g times m, which is the radius, to some power, fixed. So this is the expansion in which the geometry doesn't move, okay? And you treat gravitons as free particles or almost free particles in this background, and that's it. Okay. Now, because the entropy, if you say that the entropy is finite, okay, then there are automatically new time scales that appear in the problem, just because of the finiteness of the entropy. Some of them are local, in the sense that they occur, they characterize processes that are near horizon things. And some of them are less obviously local. So let's look, for example, first at the local ones. Right? So if the entropy is finite, you have your black hole and you have a thermal atmosphere, right? So there are energy fluctuations. And as in any other thermal system, the energy fluctuations will be of order delta E over E, T over M. Okay? And this should be of order 1 over S, as in normal systems. And when you put just the formula for what T is in the case of black holes, you get that. So because the entropy is finite, you get the right amount of energy fluctuations that you expect in a normal thermodynamic system, right? But then this raises an interesting question, which is the fact that you have all these memory effects that remember what the initial details of the collapse of the black hole was, okay? And we said that these memory effects relax exponentially fast. So you can construct now a new time scale, which I will call the scrambling time scale. this time scale will be the time scale at which the memory effects go below the characteristic level of the energy fluctuations. Okay? Yeah. No, they are very small. They very fast disappear. Yeah. Well, if you were powerful enough, you could. Yeah. But because they redshift exponentially fast, you would need to monitor the black hole with detectors which are exponentially big in order to capture these very long wavelength effects. No, these are things that are visible to you, but they are very redshifted. Okay? So they come at extremely low energies. So the scrambling time scale is characterized by e to the minus kappa t scrambling, call it like that, of the order 1 over s. And then from the relation you get that t scrambling is of order kappa to the minus 1 log s. Okay. So this is again a time scale which is non-perturbative in the expansion parameter of the effective theory, okay? Because it goes like log of 1 over lambda effective. Okay? This goes like gamma minus 1 log of 1 over lambda effective. Now, the fact that the details of the initial state go below this level doesn't mean that they disappear. You could, in principle, still detect them. Okay? After all, we get the Higgs particle out of taking it out from an enormous background, okay? Which is much smaller, much bigger than the effect that you're looking for. So, in principle, you could dig these effects from the thermal atmosphere, but this is just to indicate that very fast these effects become very, very very weak in the background of the thermal atmosphere. Now, the same time scale governs another effect, which I will call the butterfly effect. Yes? Sorry? This is my definition today. Yeah. Okay, so let's look now. Let's go back to the relaxation story, right? So I have here the relaxation zone. So at proper distance equal to kappa of order kappa to the minus 1, right? And I am watching that there is a missile that is coming from the horizon in this trajectory to me, okay? So this is the question you asked before. I'm putting it. I'm putting the stakes higher. I'm saying that it's a missile that is going to kill you, right? So what you want is to send an anti-missile in that will deflect it, okay? But let's say, sorry, right? What?
In Israel, they're very good at that.
Yes. Yeah, I will not talk about the make and mark of the missiles. Okay? So, but let's say that you can only interact gravitationally. So they are gravitational waves, okay? And then they will pass through each other. They interact very quickly, and you will not be able to deflect the object unless you shoot it early enough. So if you shoot it early enough, then the collision will occur close to the horizon, right? And if you are a guy that is sitting here at some fixed position, you will see one coming from below, the other coming from above, right? And if these guys have energy of order t here, measured by somebody who is sitting here, then the guy that is sitting here will see them with an energy which is blue shifted, right? And if the collision occurs within 1 Planck distance of the horizon, then the energy of the center of mass collision will blue shift to the Planck mass. And because gravity becomes strongly coupled at the Planck mass, then the collision will be able to deflect, in principle. Okay? So you will be able to kick it off and erase this. Right? So this time scale, which is the time scale at which you are powerful enough, your anti-missile is powerful enough to deflect the incoming missile, is what I will call the butterfly time. And this is again of the same order as the scrambling time. Okay. So why it's called butterfly? It's called butterfly because what you are trying to do is to undo something which a priori looks like a very strange state. So you may wonder, what was the missile doing near the horizon, taking so long to come out? Who put the missile there, right? Any situation in which you can imagine constructing that state is very complicated and very uneasy, okay? So you could also say, maybe it was in the Hawking radiation. But it will be very improbable to have that state in the Hawking radiation because typically the states in the Hawking radiation are delocalized over this whole region. Okay, so when you look at them, a local observer looking at them will be typically inside the particles of the Hawking radiation, so to speak, inside the wave function. Okay? So if you really want to prepare this state, what you have to do is to take the state here and propagate it back in time. Right? So you have to do something very weird, which is to prepare the quantum state here by taking an easy preparable state here and take it back in time. Right? Then that is the one that you have to use to shut down. Right? And this is why this kind of situation is related to what is called out-of-time order correlation functions. Because you need one of the operators, you need to transport it back in time and put it before the other operator that you are going to use to shoot the anti-missile. Okay? Your initial state is prepared by a time reversal operation. Yes?
This seems to be very similar to what happens in a decay. I mean, in a decay, you lose information about the initial state very quickly, and it's very difficult to reconstruct the initial state. So why does this have more scrambling?
Well, because I think it's more similar. I mean, in the decay, when you think about a decay, you think of a decay of a simple object. Okay, so we really do reconstruct the states out of a decay when we study in particle physics decays of particles. We do reconstruct the properties of the initial particle, but because they are very simple processes which involve few particles, and we can characterize very well the S matrix as a mathematical formula. Okay. Yeah, but if it is a simple state, you can do it, right? But in this case, this is more similar to the situation when you spill a cup of coffee in the floor, and you imagine in your head that you are going to prepare the state which is the time reversal of that, in which all the coffee collects itself and goes back to the cup. Okay, and then you can say, how can I ruin this state, right? By a perturbation. So if you send a small perturbation into the situation when this is collecting itself, and you do it very late, by the time, for example, the water is or the coffee is already going into the cup, you perturb that state, you will send some drops out, but the miracle will still happen. Okay? However, if you perturb early enough, when all this spread stuff is still collecting itself in this incredibly correlated situation, any small perturbation will ruin the correlation. Okay? So the butterfly time from that point of view is the time that you need in order to spoil the miracle. Okay? And there is a similar situation here in the case of the black hole. In fact, when you think of this holographically, this happening in the Hilbert space of a conformal theory, it is literally that. Right? It is literally that in terms of some state in the conformal field theory. Okay, so these are characteristic time scales that we can construct once we know that the entropy is finite, and they are quantum time scales, right? Because they, for this particular problem, they are associated to the fact that the entropy is finite. Once you have the idea that the entropy is finite, there are other quantum time scales you can consider which are kind of more exotic, right? So let's think So, for example, famously, you should be able to say in some way that the entropy is given by the log of the density of states of some Hamiltonian, and that Hamiltonian would be the Hamiltonian of quantum gravity in the sector of the states that look like black holes, right? So the very old problem of counting the microstates of a black hole are just realizing the formula of Bekenstein-Hawking in terms of this for some honest density of states, which corresponds to the eigenvalues of some honest Hamiltonian. Now, if you consider just a band of states which has a width of order the temperature, and they have some average energy E bar, okay? In a band of states of width T, you can consider the density of states as approximately constant. Okay? This is because if you take the derivative of the density of states of log of omega with respect to E, this is the derivative of S with respect to E, which is the temperature, by definition of the temperature. Okay? So the variation in the log of the density of states goes like 1 over T, the variation in energy. So if I consider energies of order T at most, I get a variation in the log which is of order 1. Okay? So within that, that width, I can consider in the first approximation the density of states as not varying much. Okay? So how many states are there in this band? There are e to the s states, where s is some average more or less in the middle of this band. Okay. And if I consider now a state which is in that band, just a linear superposition of those eigenstates. So some state in the system that looks like this, some pure state, where these are the eigenstates of the Hamiltonian with those energy levels. Then I can ask, if I start with some given state, when I get into a completely general region of Hilbert space with respect to the starting point. Let's say that all the states were prepared in some way that if I write these coefficients as a modulus times a phase, then time evolution of this state, of course, the only thing that it does is that it shifts the phase. Okay? So I get phi n minus En T psi n, or if I put here minus, I just shift the phase. Okay? So let's say that I start with a state that has all the phases aligned. Right? So in order to characterize that state, I give you e to the s clocks, right? And they are all on the same point, right? And now I just let them evolve. So the clocks start turning, and each of them goes with a different frequency because the frequencies are En. Okay? Now there is an overall rotation of the clocks which is irrelevant because I can absorb a global phase without changing anything in the physics. I can just put this as e to the minus e bar t times the sum Cn e to the minus phi n e to the minus I En minus e bar t. So this is physically irrelevant. So the important thing is the relative frequencies of the clocks, right? And if I start with all of them aligned, I can ask when all of them become more or less separated by pi, by an angle of order pi. Okay? Notice that at the beginning, if these energy levels are separated by a very small amount, in the beginning they will start running, but they will separate very little, okay? Because the differences in the energies are very small. Right? So the state becomes generic when all phases turn on average. And that means that you have to look at the minimal frequency separation and find what is the time inverse of that, okay? Because that's the time you need in order for two phases that are separated the smallest, to become separated by order pi, okay? And that time scale is th times the average frequency of order one over the minimal energy separation. But the minimal energy separation is of the order of, sorry, let me write it here. So that time scale is of the order of the inverse of the minimal energy separation. Okay. But this is of the order of the average frequency inverse. Sorry, yeah, the average frequency inverse times e to the s. Okay. So there are e to the s states here, and therefore the typical energy separation, the average, the minimal energy separation is of order of t, which is the width of the band, e to the minus s. Okay. Now t is also the average frequency of the e to the s clocks, right? Because they run the average, the average energy difference of the e to the n clocks to the average energy, because they run at different velocities, but the average difference is just something of order the width of the band, which is t. Okay? So I get this scale, which is just t to the minus 1 e to the s, which I call the Heisenberg time. So the Heisenberg time is the typical time scale for a generic quantum state to become generic as it evolves in the big Hilbert space. Okay? It is the same. So that's the. There is what? The time energy uncertainty is this one. Well, you can say it is. I don't know if it is time energy uncertainty. I don't. The scale is the same, but I don't want to say that, right? Like a what? No, I don't think so. Well, I don't know. Okay, so now this is also a non-perturbative time scale, because again, this time scale goes like t to the minus 1 e to the 1 over lambda effective. So in effective field theory, it's non-perturbative. Okay? We don't see it in effective field theory. And finally, there is another time scale, which is similar to this one, but even more crazy, which is the Poincaré recurrence time scale. So now you look again at your e to the s clocks, and you ask, when do they come back to the previous position? All right? So we just wondered when do they become completely spread in the relative angles, right? Now you are already in that regime, so your clocks are sort of randomly distributed over the whole sphere. And now you can ask, when do they return? When typically they return to the previous position. Now, if the energies have rational relations between them, then the system will be periodic, and the period will depend on the denominators of these rational relations. Okay? So that would be whatever it is, right? But if the energy levels don't have rational relations between them, which is the generic thing, because the energy levels don't have to have rational relations between them unless there are some special dynamics in the problem, then the system will not be periodic. They will never return. But then you can ask if they return within some epsilon, right? So you can ask if they return within some tolerance. So given epsilon, which is, for example, some differences in angle divided by 2 pi, then you can ask when they will all return, right? So if you consider the full set of configurations of the e to the s clocks, this forms a torus, right? So it forms a torus in e to the s dimensions. And the clocks will be back to the original position within epsilon precision if they are in one of the epsilon cells in which you can divide the torus with this volume. So if an epsilon cell of configuration space has a volume of order delta alpha over 2 pi to the e to the s. Okay? Yeah.
You're saying volume when you have a continuum of energies.
No, I don't have that.
Okay.
Yeah. Yeah. I have a band, right? So I have a band, I have finite entropy, which means that I have a discrete spectrum, right? And I'm just defining things under that assumption. Yes, yes. So I am giving a system which has entropy S. Actually, this works for any system, as you see, right? And I am just asking what are these time scales associated to states that are generic, defined in this band, with superposition, a generic state which is defined with superposing the states of this band. Okay? It's just a number. It's whatever. It's e to the s, because when you think that S is the entropy of the black hole, it's very impressive what comes out. But it could be 3 or 4, whatever. Right? There's nothing peculiar about this. This is just completely general for any band of states. So if you now consider looking at the configuration of the clocks after inverse frequency time, and the typical inverse frequency, which is t, right? T to the minus 1. So you make a picture of the clocks. Then a time of order inverse t later, you make another picture of the clocks, and so on. Right? So at some point, you may find that the clocks return to your initial cell. Right? Then you're finished. And then you can ask, if I'm not lucky, how long I have to wait in order to be sure, for sure, that the clocks will return? Well, you only have a finite number of cells in your configuration space with size epsilon, so you have to wait a time which is of the order of the number of cells that you have. Okay? And the number of cells is of order 1 over epsilon to the power e to the s. Right? So the time to return, the Poincare time, is t to the minus 1 times 1 over epsilon e to the s, which is t to the minus 1 times e to the log 1 over epsilon times e to the s. Okay, which is a completely ridiculous time scale. And this is ridiculous even for systems which are very small, right? For systems which are 10 particles, for example, this is already ridiculous, right? Now, this time scale, the Poincare time scale, is different from the previous time scales I considered up to now. The previous time scales were intrinsic to the dynamics of the problem. They didn't depend on any coarse graining or any characterization a priori that is given by the observer, right? But this one depends on epsilon, so it depends on how precise I want to be the return, right? So this is not an intrinsic time scale, but it depends on how accurate I want, what is the tolerance that I have for monitoring the state return, okay? Whereas the other ones are genuinely dynamical scales that are intrinsic to the dynamics of the problem. Okay. So now you may wonder, so why are you worrying about this thing? Because it's obvious that e to the s or e to the s is completely irrelevant for a problem in which you are going to to worry about the evaporation of the black hole. Okay? It's completely irrelevant, no? Also, if the black hole evaporates in infinite space, then the spectrum of the theory is not even continuous. So you cannot set up these kind of scales rigorously if you are working in infinite space, right? Because the radiation will go out and will explore more and more the lower parts of the spectrum, each particle, right? So you have an arbitrary set of states below every energy that you give, any finite energy. Arbitrarily large, a continuous set of states. So these spectral characterizations look totally irrelevant to this problem. And what I'm going to tell you now is a standard line of argument to remind you that this is not probably correct, or that, in fact, we should worry about these time scales eventually. And this has to do with the issue of the so-called information retention time. Okay? So again, this is something very well known. So you have now the black hole evaporating, and you ask how long you have to wait until the information starts to come out from the black hole. Okay? So the black hole is here. It's emitting particles of radiation, and you are collecting them. So you can see the system as partitioned into two parts. Just thinking naively, you have the black hole part, and you have the radiation part. And the separation between the two is movable. The radiation part is growing, and the black hole part is shrinking. Okay? So every quantum of every Hawking quantum, when it comes out, comes in a thermal spectrum, so it comes with entropy of order 1. Right? It looks like it is entangled with something that is left in the black hole with an entanglement of order 1. And in the approximations of Hawking, there is no correlation between the emissions of quanta at different times, because you are not taking into account the back reaction. Okay? So every emission is independent. So if you make a plot of the radiation entropy as a function of the energy of the radiation, what you get at the beginning is just that this rises linearly with the number of quanta that come out. Okay? Let's say that you define this entropy as the fine-grained von Neumann entropy of the density matrix of the radiation. Because I have the system in two parts, I can consider just the density matrix corresponding to making observations on the radiation. And let's assume that the initial state was a quantum pure state. Okay? And let's moreover assume that the dynamics is unitary. So it's a pure state at all times. So I have a pure state at all times, which I observe partially, and I defined a density matrix for the part of the system that I am observing. And then I compute this for all of them, and the calculation of Hawking tells me that at least within the approximations of his treatment, this function will rise linearly with the number of quanta that you're emitting. So this function will behave just like a normal thermal entropy. Right? However, the problem is that, of course, the approximations that involve Hawking calculation, because they were effective field theory, they are going to break down only when the effective expansion parameter is of order 1. And that's when the black hole is of Planckian size. So this, according to Hawking, should follow like that until the very end, when all the radiation, all the mass of the black hole came in the form of particles, right? And then, if this function is going to come down to 0, because assuming unitarity, if the initial state was pure, the final state has to be pure, and therefore the entropy has to be 0, all has to come at the end. Okay? So this is the famous information paradox, why this function continues rising so that it puts you in this incredible situation in which you have to take out all the information at the very end when you only have a few quanta left for emit. Okay? And well, the resolution of this is that maybe Hawking made a mistake. Okay, that's one possibility. And this function actually is different. So for example, this function could be something like this, right? The question is how different it is, or how much of a mistake Hawking did. Okay? And there is an amazing situation which occurs because you are looking at very large Hilbert spaces, which actually shows that, in fact, the mistake made by Hawking could be extremely small. So it could be actually non-perturbative in the expansion parameter. So in fact, you could say that he didn't make a mistake in that case because within the rules of the game, which was effective field theory, he didn't make a mistake. Okay? So the question is, could be that the corrections to this function are very small so that it cannot be visible in effective field theory? Okay? So to illustrate this, I'm going to use a simple model, which is drawn from an analysis that was done a long time ago by Don Page, in which he considers a situation where this partition of the system into black hole and radiation is not following, if you like, strictly speaking, the rules of the game, but is assuming that the state of the black hole is completely random. Okay? Yeah.
How this calculation can be done in field theory? So what do you mean by effective
Effective field theory is just free fields in the background of the black hole, right? The back reaction cannot be incorporated easily, at least not perturbatively. So what you do is basically you assume that the function is given by the thermal entropy that is accumulated in each Hawking emission, and you just change adiabatically the temperature according to the fact that the black hole is shrinking. So in fact, this curve starts linear, but then it grows because the temperature goes up. For smaller black holes, the temperature goes up. So Hawking calculation is that this is ER over T, more or less. And where T is going down, this goes up a little bit more. Okay? So let's assume that the complete state is completely random at all times. Okay? This is completely unreasonable because, as I just told you, if you start with a particular state, like for example the one which made the black hole, which is not a random state, okay, you have to wait a Heisenberg time, which is exponentially large in the entropy, in order to randomize the state in the Hilbert space. Okay, so that's much longer than the evaporation time. So during the evaporation, the black hole doesn't have time to become generic as a state in the Hilbert space. Yet, let's assume that it does somehow, okay? Or that let's assume that you consider a system in which this happens, okay? And then let's ask how much this density matrix can differ from the completely mixed density matrix in that situation. This is the kind of question that was investigated by Page, and then what he found is the following. Let's consider, for example, in order to understand it, to get an intuition of what is at stake, let's consider a state which has the form of the following form. So I have a sum Cn, Ci1, In, I1, In for a system of n qubits or n spins. Okay, and this is the basis, which is just the product basis for all the individual spins. And I consider a state which is generic, which means that typically since I assume that it is normalized, then the sum of the squares of the c's should be 1. There are 2 to the n terms in the sum, so that means that c is of order 1 over 2 n halves. Okay? So I'm going to take the case in which the c's are all equal, just to simplify life. So the state is of the form 1 over 2 to the n halves, the sum over all the faces times the basis vector. Okay, and these faces are random. And now we select k of them, k spins, and construct the relative density matrix coming from tracing over the rest. Okay, so you construct rho from I1 to Ik, J1 to Jk, which comes from tracing over the n minus k rest of the spins. Okay? Now, you can calculate very simply what is this density matrix, and it's given just by 1 over 2 to the n, the sum over alpha 1, alpha k plus 1, alpha n, e to the minus I theta I1, Ik, alpha k plus 1, alpha n, plus I theta, j's, and the alphas. Okay? So these thetas have i's here, j's there, and they share the alphas, and they are summed over. Now, because these phases are random, you are summing random phases. The typical value of the sum of random phases is like summing plus or minus 1 at random, say with n trials, you get a random walk. Okay? And the size of a random walk scales like the square root of the number of steps. So the typical size of this thing is the square root of the sum of terms in the sum. Okay? Unless all these phases exactly match each other and you get a sum of ones. And this happens for the diagonal terms. So the diagonal terms, these phases are 1, so you are summing over k minus 1 terms, so you get 2 to the k minus 2 to the n minus k from the sum, so you get 1 over 2 to the n, 2 to the n minus k, times the identity in k spins, and this is just 1 over 2 to the k, the identity in k spins, which is just the maximally mixed density matrix. Okay? So this is the analog of the Hawking answer. Okay? The entropy of this density matrix is just k times log 2. So it's proportional to the number of spins that you have collected, and this is analogous to the number of particles that have been emitted.
This density matrix is not normalized.
Yeah, it is 1 over 2k. Yeah.
1 over 2k, but the identity is k cross k.
Sorry, 2 to the k. Yeah. Okay. On the other hand, the off-diagonal terms, the random phases don't cancel out, and then when you estimate them, what do you get? When you estimate them, you get the off-diagonal terms, you get something that is of the order of 1 over 2n times the square root of this thing. So you get 1 over 2n times 2 to the n minus k halves. This is something of the order of 1 over 2 n plus k. Halves. Okay? You can also write it in this form. You can write it as 2 to the minus k 1 over, or 2 to the minus k 2 to the minus n minus k halves. Okay? So you see that this exponential is small when n is large. Okay? So they have diagonal terms, which is the difference between the maximally mixed density matrix, what is the analog of the Hawking result, and the exact answer is exponentially small. Okay? Now, I can write this, since this is k is the number of spins, which is analogous to the number of particles that came out. This is proportional to the time it elapsed since the evaporation began. Okay? So this is something that scales like e to the minus some characteristic quantity of the problem, I will call it kappa, t. Right? And this thing here scales like e to the minus the entropy of the remaining state that still didn't evaporate, which is the remaining black hole. Right? So this is case like this times e to the minus a constant, the entropy of the black hole at time t. Okay? So this is exactly what you expect if you imagine that the physics that takes the information out of the black hole is non-perturbative. Because this thing here is a non-perturbative effect on the black hole when it has this size, the size after time t, is something of order 1 over lambda effective for that black hole. And this is the scaling of the memory. So this is how the effects of the initial state are felt after time t. So if you had a mechanism that has to transfer the information in the memory into the Hawking quanta, okay, you could imagine that if that mechanism was non-perturbative, it would have this form, this scaling. But this is exactly the scaling that you get in this problem. Okay? And in this problem, we know what happens at the end. What happens at the end in this problem is that if you plot the entropy of k spins, it goes up until when you reach n halves, and then it goes down again until you reach n. Because the initial state was pure, the final state has to be pure, and it has to go down again. Now, the difference between the exact pyramid form, which is what you get just from this term, and the real thing is just this off-diagonal term, which is very, very close to it all the time, is exponentially close to it. Okay? So, in the page problem, you had to assume to have this very strong assumption that the black hole was a perfect randomizer, which is not reasonable, actually. But the answer that you get has the same scaling as you would imagine you would have in a system in which the memory effect is exponentially small, okay? Which we know happens for the case of the black hole. Right? So this is the reason why people think that, in fact, what happens with information in black hole physics is that it is non-perturbative effects which are beyond effective field theory that brings the information out. And there is no need for things that are so strong as, say, powers of 1 over s, powers of Newton constant in order to get the information out. Because you can do it in principle with effects so small as exponentially small in the entropy. Okay? In fact, you get something which scales just in the way that you expect should scale. Right? As an exercise, you can check, for example, that if you compute the entanglement entropy of the k spins by taking the minus trace rho k log rho k, okay, what you get is just k log 2 plus something of order 2 to the 2k minus n. Okay? This is valid when k is smaller than n halves. So you see that the correction is exponentially small until you get exactly to the middle, to n halves, and then in this case the correction is of order 1. So the idea that the entropy of the radiation is just given by the thermal entropy of the particles that you have emitted is wrong by order 1 precisely at mid-time, according to this model. Okay? So at this point is when the prediction of Hawking and the exact answer starts to differ by order 1. So effective field theory breaks down at this time scale, which is the information retention time scale. Right? Okay, so why is this interesting for the problem? Well, what is relevant here is that e to the minus s effects are responsible for the solution, let's say, or the in this type of a scenario of the information paradox. Okay? But e to the minus s effects are the effects that are responsible for the splitting of levels in the spectrum of the black hole. Okay? And are the ones that are responsible directly for the Heisenberg timescale and the Poincare timescale. So this problem is not going to be solved just by looking at it in the real situation, because you are not going to be able to do these calculations in the original problem. Why? Because the original problem really, rigorously, is an S-matrix problem. You make the black hole, you wait for it to evaporate, you collect all the data, but you have to collect the data of order S particles. And our control over the S-matrix of quantum gravity, even in the case that you think of the string theory or whatever, is not to the level of being able to extract information for that complicated situation for order S particles. Okay? Even if we knew things about 2-to-2 scattering, for example, exactly, this is a totally different kind of game. So one thing you can do is to simply change the problem, okay, and get rid of the evaporation. And let's say that the black hole doesn't evaporate because you put it in a box and you make it equilibrate with Hawking radiation. Okay? So in that case, you don't have to worry about evaporation. Now the black hole will not disappear. But now you can talk about the Heisenberg scale and the Poincare scale. And these scales are directly related to the energy splittings of the levels of the spectrum of the Hamiltonian, which precisely are responsible for these effects. Okay. So the idea is that by putting the black hole in a box and studying with high precision physics that depends on the e to the minus s effects, you are addressing the same problem that is supposed to solve the information paradox in this situation. Okay? If the information paradox is solved by 1 over s effects, so if the information paradox was to be solved by some effect which is much larger than non-perturbative, then this situation is not interesting for us, in the sense that we don't expect to gain any knowledge about that physics by just putting the black hole in the box. Okay? But if the conservative scenario that information flows out of the black hole by non-perturbative e to the minus s effect is correct, then you expect to gain information about that problem by just putting the black hole in a box and looking at properties of the physics which depend precisely on the finiteness of the entropy. Okay, so just to finish, in the few minutes that are left, I'm going to just set some notation for tomorrow. Because, of course, how can we put a black hole in a box? Okay, so we can ask this question in general. How can a black hole come to equilibrium in a box? This is a non-trivial question because black holes have negative specific heat, so they tend either to grow or to shrink when you consider them in equilibrium with radiation. Okay? So it's a non-trivial question if you can maintain them eternally inside the box in equilibrium without either crashing the box or shrinking to zero and leaving just radiation in the box. Okay? So this is a problem that you can study as an exercise. You put a black hole in a box and you study just crudely equilibrium states of these two components. You just model it in the following way. The total entropy of the system you can regard as made of two components. There is the black hole component, which is given by the black hole entropy, which in terms of the mass has this form in d plus 1 dimensions. And then there is the radiation part, which is the total energy minus m to the d over d plus 1. And then you can study if there are equilibrium situations for this problem. And you find that there are if the energy is sufficiently large. So if this energy, total energy, is sufficiently large, there are situations where a black hole can sit there and stay in stable equilibrium. In order to find that, you have to plot the entropy as a function of m, and you have to find a situation in which you have a local maximum of the entropy dominated by a black hole. Okay, like this. So this point here is no black hole because m is the mass of the black hole. So this is full radiation. This is full black hole, and in between you have configurations. You have black hole with some radiation. Here you have an equilibrium situation, but it's unstable, right? So if you put the system here, any fluctuation will either make the black hole grow or will make the black hole shrink and leave only radiation. This is a very simple problem that you can study, right? And you will find that it has a solution. You can characterize some critical energy. Which is of the form 1 over L, with L is the size of the box. 1 over L times L over L Planck to the d squared minus 1 over 2d minus 1. And above this energy, black holes exist inside the box, taking almost all the energy. Okay, so they dominate completely the energy of the system, although their size is not enough to crash the walls of the box. If you continue putting more energy into the system, the black hole will grow and will crash the box. This happens when you hit the maximum mass of the black hole, which is about L to the d minus 2 over g. Yes? Sorry?
Where does the length of the box appear in the formula of the entropy?
Yeah, very good. It appears here. Sorry. Okay. So when the black hole becomes of this mass, it crashes the box, right? So you cannot consider arbitrarily high energies in this problem. But fortunately, we have a box which does, right? There is a famous box that does. The reason why you cannot consider this case is because you don't know how you made the box, right? So you have to worry about the energy momentum tensor of the box. Nobody knows how to do that, except for one case. There is a particular box whose energy momentum tensor is known, which is ADS. And the energy momentum tensor is very simple. It's just a negative cosmological constant. So what you have in ADS is how much time I get? 1 minute? Oh. So in ADS you have a region of size L, which is approximately flat, okay, where L is the radius of curvature. And the rest is all walls, right? So the walls are infinitely thick. And in ADS space, as you know, what happens is that if you throw a stone, the stone comes back to you. Okay, so it has a harmonic potential. If you just write down the solution of Einstein equations for ADS, this is one way of parameterizing it in polar coordinates. You see that the time-time component of the metric is -1 minus twice the Newtonian potential, and that means that the Newtonian potential looks like 1/2 r squared over L squared, so it's a harmonic potential. So the ADS is a harmonic trap. Okay, this is what is normally drawn in time. So this is ADS in time. As saying that if you throw a stone, it will just oscillate, come back like that. Okay? And if you throw a stone harder, it will go further up towards the infinity, but it will take the same time in coming down because it is a harmonic oscillator. Okay? So there is a natural time scale for the box, which is L. But in this case, it's not the time scale for bouncing off the wall, but it's the time scale from bouncing off a harmonic potential. Okay? Now, if you put black holes inside ADS, then the metric is just the same as before, with a simple modification of the function, of the profile function, which is just 1 plus r squared over L squared minus mu RD minus 2. So this is, you get the same situation as before. It's just like a combination of the background vacuum solution and the Schwarzschild solution, right? Very simple, with the same mu as before. And then you see that there are two types of black holes. There are the black holes which are very small, so they are sitting inside the box, squarely inside the box. They are smaller than radius of curvature, and they are, for all purposes, like Schwarzschild black holes. And there are, of course, the large black holes, which are entrenched in the walls. They are touching the walls. Okay, they are eating the walls, actually. They never end eating the walls, but they are eating the walls. And those are the ones in which the radius, the Schwarzschild radius, is much larger than L. Those are the large black holes. Now, for those black holes, the relation between the radius and the mass is different from before. So now what happens is that the radius goes like mu times L squared, radius to the power d. Right? This is for large black holes. And the very famous result is that if you compute the entropy just from the Hawking-Bekenstein formula, what you get is n star LT d minus 1. Where n star is just L over L Planck to the d minus 1. And this formula is just the formula for the entropy of a system of n star massless fields sitting in a box of size L in quantum field theory. Okay? So this is one of the ways in which you can guess that there is a dual description of the whole system in which you have a conformal field theory in one dimension less. Right? So we get, in this way, a bonus. We have, not only we have a good box, but we also have a dual description of the box in which we understand the physics in principle in terms of a known system, which is a conformal field theory. However, the conformal field theory that we need is very exotic. Okay? It's not a conformal field theory that you find easily. We use ADS-CFT all the time, but we tend to forget that very few examples of ADS-CFT are known, and in fact we don't know how many there are, and there could be just there is only one example basically, which is n=4 super-Yang-Mills and all the Cassin theories which are based on the same amount of supersymmetry. Why is that so? Because if you plot the logarithm of the density of states that this conformal field theory should have, okay, as a function of the energy, here is 1 over L, which is the gap to the ground state, because you are in a box of size L. Then there is the band of energies, which corresponds to these large ADS black holes, which have an entropy corresponding to a typical high energy state of the conformal field theory. So let's say, for example, a quark-gluon plasma. They have this scaling for the entropy. So not very mysterious. And in a normal conformal field theory, even a conformal field theory with large number of fields, this is all you have. The moment you put your system above the gap, you enter into a regime in which the entropy scales like this, the density of state goes like that, and that's it. However, in an holographic theory, if you want to put their stuff inside the box, you need room in the density of states to accommodate small black holes, to accommodate strings, to accommodate gravitons propagating there, etc. So if you put here in this band of energies, this intermediate band of energies, all you need in order to work the dictionary of ADS-CFT and say that you are studying black holes in the CFT, you need a band, for example, for the graviton states. They have this form where the density of states goes like EL to the d over d plus 1. And then you need another band for black holes, which are small. And this, when you write it down in terms of the CFT variables, goes like this: 1 over n star d minus 2 LE to d minus 1 over d plus over d minus 2. This is the band of energies which corresponds to small black holes. And this is the Bekenstein-Hawking formula for the black hole, the normal one written in those variables with this n star there. And this here is the large black hole band, which corresponds to something which is normal. So it's n star 1 over d, e times L, d minus 1 over d, which is the normal scaling for the higher density of states of a conformal field theory. So you need all these exotic bands in order to have a working box. Okay? I forgot the strings, yes. Yeah. There are all kinds of bands here that you could put, but I will just simplify life and consider just this very simple situation tomorrow. Okay? So tomorrow, what I'm going to do is to just forget about this sort of introduction of confusions of 30 years of the problem of information and paradox in black holes, etc. Sit squarely, if you like, in the context of ADS-CFT and ask what kind of property of the low energy effective field theory in the interior of the bulk description of ADS-CFT, of the gravity description, what type of property misses completely the recurrence time scale and the Heisenberg time scale. And on the other hand, what general lessons we can get about the physics associated to these time scales from the conformal field theory. Okay? So the idea is to look at some observable which is simple, like a correlation function, and study it at very long times, in which you reveal the dynamics which is appropriate for these time scales, and see what is the difference and what are the possible, if you like, modifications that you could do to the bulk dynamics in order to account for this behavior. Okay? And what we will find is that there are properties in the structure of the time scale of these correlation functions which are related to the assumption that the conformal field theory should be chaotic, for example, which are characteristic, and when you study them for a system that has this type of density of states, you find that you can get information, or you can extract, if you like, looking at the very long time behavior of the correlation functions, you can extract information about these intermediate time scales, sorry, these intermediate energy bands, okay? Which is, if you like, the physics of the bulk dynamics, which is just well confined inside the interior of ADS. All right, that's all for today. Thank you. Which questions? The questions about the evaporation? No. No, look. No, you can put a small black hole inside ADS and let it evaporate. You are not going to be able to solve the problem, okay? In the sense that you don't have a a very careful description of that state in the CFT. Right? So you cannot test this scenario really on those grounds, except just saying that the problem, unitarity will be preserved, okay, just by the rules of the game, but you will not be able to test, for example, explicitly exactly how it goes, etc. Right? That's true. So I forgot already about the evaporation problem. I used the evaporation problem just as a motivator to start to look at effects which are of order e to the minus s. Okay. So I'm going to start to study effects of order e to the minus s in ADS-CFT as a way of extracting information out of very long times. Okay. And I'm going to just appeal to this discussion today as a motivation for that. Okay. So I'm not going to solve the information problem. In fact, you can, if you're optimistic, you can say that you are rephrasing the problem of information in another situation, because in this case, what you're looking is at correlation functions. You have a black hole there. The black hole will not go away, but a correlation function can be interpreted as perturbing the system and seeing how this perturbation diffuses into the system and how you can recover the information about the initial perturbation later on. Okay? But it's about a perturbation. It's not about the original problem of S matrix, if you like, of operation of the black hole.
Okay, you have a question? So, I don't, if you follow the program every day, we made a change. There was a reason for a change, which said that you should immediately have the don't show, but that reason, unfortunately, is not here. So we're going to have now a break in your old program. And we need half an hour. And please do